So I will be talking about testing cosmological fields with gravitational waves. But before doing so, I would like to introduce first the underlying theory, which is general relativity, and how we use it in order to explain the cosmological observations. I will be introducing general relativity from different perspectives, but I would like to start with the picture of Einstein, because thanks to him, since 1915, we have the theory of general relativity. And when he constructed his theory of general relativity, he postulated that gravity is a geometric property of space-time. So it's really just given by the property of space-time, and gravity is geometry. So imagine you start with a flat space-time, and now you put a massive object in this flat space-time, and due to the mass and energy of this object, the space-time gets curved. And now if you have a second object like the moon, it feels the gravitational interaction because this space-time is curved. So it's not anymore like in Newton's physics that there is a force that propagates instantaneously from Earth to Moon, but rather the interpretation that this four-dimensional space-time is curved. So general relativity equals curvature of space-time. I would like to introduce a provocative question. Is this geometrical interpretation of gravity unique? And I will answer this question with a no and introduce a Trinity formulation of general relativity, where I will show that the same theory of general relativity by means of this geometrical interpretation can be actually formulated in three completely equivalent ways. So this will allow me to bring you can see this here somehow. I don't know how to remove that. Anyways, so geometrical trinity of general relativity. I will start with the standard formulation that you might be already quite familiar with, based on curvature as Einstein formulated, but then I will introduce a second formulation of general relativity, this time based on torsion. This is the teleparallel equivalent of general relativity. And then finally, I will move on and introduce a third completely equivalent formulation of general relativity, and this time based on non-metricity. What do these geometrical objects represent? You might be already familiar with what curvature represents. So imagine you have a vector here pointing towards a given direction. And now if you move this vector along a closed path and you come back to where you started, and if this vector points towards a different direction than you started with, it means that your space-time has a non-vanishing curvature. How about torsion? Now, if you have two vectors and you parallel transport them along each other, and if this parallelogram doesn't close, it means that your space-time has a non-vanishing torsion. Similarly, now, if you have a vector and you move it along a given path, if the length of the vector changes, it means that your space-time has a non-vanishing non-metricity. These are what they represent physically. These are different physical properties that a space-time can have. Let me start with general relativity a la Einstein. There, the fundamental, so we are in a pseudo-Riemannian manifold, and the fundamental object is the metric, the symmetric metric G mu nu. And the connection is just given by the Christoffel symbols, which themselves are completely determined in terms of the metric in this form here. So there isn't anything additional new to the connection. And so you are now living in a space-time which is torsion-free, non-metricity free, but it's curved. So you have this non-vanishing Riemann tensor, which represents curvature. Its expression is given here. You see that you have some derivatives acting on the Christoffel symbols, and you have some Christoffel's squared part. Here, because you have derivatives acting on the Christoffel symbols, you will have second derivatives acting on the metric. But this is a tensor with 4 indices. You can contract them, build a scalar quantity, and this uniquely gives Einstein's Lagrangian, the Einstein-Hilbert action, as you might have seen already. As I said, because of these derivatives acting on the Christoffel symbols, you have second derivatives acting on the metric. And now if your manifold has a boundary, then the variational principle is not well posed due to this second derivatives acting on the metric. And you need to introduce the Gibbons-Hocking-York boundary term by hand in order to compensate those second derivatives acting on the metric, which is going to be something different in the other formulations that I'm going to introduce. Let me then move on to the teleparallel equivalent of general relativity. This time you are in a manifold which is based on torsion. Now your fundamental object is not the metric anymore, but is the connection. And this connection has this important piece here, the contortion tensor. Now you live in a space-time which is completely flat. So you are imposing the flatness condition. But non-metricity is still 0, and torsion is the only quantity that is not vanishing here. Here is the definition of the torsion tensor. As you can see, it's the antisymmetric part of the connection. As you see, it's a tensor with 3 indices. We cannot contract them at linear order to build a scalar quantity. So we need to go to second order in the torsion tensor in order to build a scalar quantity. But because it's antisymmetric in this mu nu indices, at quadratic order, we will have 3 independent contractions. Let me write them down. 1, 2, 3. So this is 1 contraction, second, and third. These are the 3 independent contractions that you can have at quadratic order, with some arbitrary coefficients, C1, C2, C3. With this, you can write an action. You have your quadratic torsion scalars. And now with Lagrange multipliers, you have to make sure that curvature vanishes and non-metricity vanishes. And only, really, let me emphasize, only if you choose these 3 coefficients, parameters in this very specific way, you obtain an equivalent theory to general relativity with the same type of dynamics and with the right dynamical degrees of freedom, namely 2. And if you want to relate it to the Ricci scalar of the Einstein-Hilbert action that we had seen in the first Einstein formulation, you see that they are equivalent if you choose these coefficients in this very specific way, up to boundary terms, up to some total derivatives. So at the level of the equations of motion, they give exactly the same equations of motion, but at the level of the Lagrangian, they differ by boundary terms, these terms here. Let me then introduce coincident general relativity, this third geometric formulation of general relativity. It has quite some interesting properties. This time you have a manifold which is completely based on non-metricity. Your fundamental objects are both the metric and the connection. And the connection, again, is completely general, arbitrary, has nothing to do with the Christoffel symbols, has this important piece here, which is the disformation tensor. This time you live again in a completely flat space-time, curvature vanishes and torsion vanishes. And the only non-vanishing tensor is the non-metricity tensor. In case you have never heard this non-metricity tensor, what this is the definition of the non-metricity tensor. So it's the covariant derivative with respect to this general connection, independent connection of the metric that applies on the metric. This is the definition of the non-metricity tensor. It's again a tensor with 3 indices. We cannot build a scalar quantity at linear order. We have to go to second order. But this time, these are symmetric, right? In the mu indices, because the metric is symmetric. Therefore, you will have now 5 independent contractions at quadratic order. I didn't even bother to write them explicitly, but there are these 5 independent contractions with 5 arbitrary coefficients, C1 to C5. You can then with this write your action. So you have this quadratic non-metricity scalar with these 5 coefficients. And then with Lagrange multipliers, we again make sure that curvature vanishes and torsion vanishes. Again, if you choose the 5 coefficients, these parameters, in this very specific way, you obtain an equivalent theory to general relativity with 2 propagating degrees of freedom. But the interpretation is very different, and the fundamental objects are very different. The space-time has a very different property. So here is the quadratic action chosen with the coefficients in the very, very specific way, such that you have general relativity. If you want to relate this again to the Ricci scalar of the Einstein-Hilbert action, you see that again they are equivalent up to some total derivatives. Okay, so this was then the third geometrical formulation of general relativity that you could have constructed if you are following this geometrical perspective of gravity. And one very specific property here in this non-metricity formulation is the following. The fact that you have imposed that curvature vanishes, so that you have flatness everywhere, and that you impose that torsion vanishes, that makes that the connection becomes pure diffs, and you can choose them, so you can fix it by means of a gauge choice, and you can put it to 0. And when you do that, when you choose this very specific gauge, then this quadratic non-metricity scalar becomes just the Christoffel squared part of the Einstein-Hilbert action. Remember, I was showing you that the Einstein-Hilbert action had one piece, which was having one derivative acting on the Christoffel symbol, and the second one, which was quadratic in the Christoffel squared, quadratic in the Christoffel symbols. And you see that in the specific coincident gauge, this non-metricity formulation just gives you the Christoffel squared part. So there is no need for the Gibbons-Hawking boundary term for a well-defined variational principle, because you don't have second derivatives acting on the metric. There's also a more direct contact with the particle perspective of gravity, which hopefully I will illustrate in a few minutes. And this improved action principle can also make some differences in consideration of energetics, thermodynamics, and quantum theory. This is something that we are investigating at the moment in our group. Okay, so this was now the pure gravity sector. And I have shown you that you can formulate the same theory of general relativity in these 3 completely equivalent ways. How about the coupling to matter fields? The coupling of matter. We know that we just don't have pure gravity, but we also have matter fields, right? So you might be aware of the fact that the very same construction of general relativity, when Einstein constructed it, relies on the fact that matters follow the minimal coupling principle. Minimal coupling principle states the following. If you have some gauge fields, some photons, they live on some flat space-time, you can promote them to curved space-time simply by promoting the Minkowski metric by a general metric, and the partial derivatives by a covariant derivative with respect to the Christoffel symbols. And so all the matter fields couple then only to the metric, but never to derivatives of the metric. This is the minimal coupling principle. And so all the matter fields couple exactly in the same way, just minimally to the metric. And that's why we have equivalence principle, right? What happens if you now naively try to apply this minimal coupling principle to the torsion theory? You see that it doesn't work. So the minimal coupling is not preserved even for gauge fields, because you have this non-minimal couplings of the gauge fields to the torsion tensor, which is something that we have never observed, right? This would be immediately ruled out. So minimal coupling principle doesn't work in the teleparallel equivalent of GR. If you try to apply it in the non-metricity formulation, it works. Gauge fields follow exactly the same geodesic equation, same type of trajectory as in standard general relativity. This was now just for gauge fields, bosons, like photons and things like that. For fermions, the situation is even worse if you have torsion in your gravity theory, because fermions really want to couple to torsion. So concerning the equivalence is preserved between these two formulations of standard general relativity and the coincident general relativity. But as soon as you have torsion, the equivalence is really very hard to get, unless you are willing to impose it in an artificial way by hand. Okay, now I would like to change completely the perspective, and I would like you to imagine a universe in which Einstein did not exist. And well, I know this would be really, really sad if he didn't exist, because thanks to him, we have the theory of general relativity since 1915. But nevertheless, imagine even if he didn't exist, at some point we would have had a modern version of Einstein. And this modern version of Einstein, okay, could be a man, could be also a woman, doesn't matter. What is important is that he or she would have learned all the standard techniques of particle physics, the way how we describe photons and electrons, right? So he or she wouldn't have cared at all about geometry and whether it's curvature, torsion, or non-metricity. So we would have constructed general relativity, definitely, maybe 40 years later, but we would have described it as a particle. So in the same way as we described electromagnetic interactions due to an exchange of a photon particle, we would then describe the gravitational interaction due to an exchange of a graviton particle. And now that's so far good. And what type of particle would this be? Would this be similar like the photon or like the Higgs field? What type of particle would this be? We can actually see immediately what type of particle it has to be by remembering what type of observational knowledge do we already know about gravity. And then we can rule out certain candidates. So facts that we know about gravity. We know gravity is long range. So if there is a particle associated to it, it should be massless, or it should have a super duper tiny mass. We know it exists as a classical theory, so it cannot be like electron-like. And so this only leaves bosons of spin 0, 1, 2. We know that it's attractive, so it cannot be photon-like. So it shouldn't give to repelling forces. And it interacts with light. So it cannot be spin 0 particle like the Higgs field. And this then uniquely leaves out the massless spin 2 particle as the candidate if you wanted to describe general relativity in terms of this particle perspective. Okay, let me represent this particle by this h mu. This h mu is my massless spin 2 particle, and I need to create its Lagrangian. It's the theory underlying this particle. So what I would do is I would just start at quadratic order in this, this massless spin 2 particle with some derivatives acting on it. So I would start with quadratic order in partial h and try to write down something like a kinetic term that would give rise to dynamics to this massless spin 2 field, right? In fact, so you can have these arbitrary contractions at the quadratic order. You have to fix these coefficients in this very specific way in order to really have two physical propagating degrees of freedom. Now you have your propagator at the quadratic order. Now you can take this Lagrangian and you can compute from it its own stress energy tensor, the chi mu from this quadratic Lagrangian. And then you couple it to itself via h mu, chi mu. And in this way, you can then obtain cubic vertices. Now you take this as your new Lagrangian and you compute the chi mu alpha beta, the self energy at next order of this Lagrangian. And then you couple it to itself again. So you can do this bootstrapping. But when you do that, you realize this series never stops. It's an infinite series of interaction. So this massless spin 2 particle has this infinite series of interactions. But you can resum them. And when you resum this infinite series of interaction, you obtain the Christoffel squared part that I was showing you in the coincident general relativity, so in the coincident gauge. This was the reason why I was saying that the coincident general relativity formulation has a more direct relation to the particle representation of gravity, because when you resum this infinite series, you exactly get the action of the coincident general relativity in the coincident gauge. But you can, as I showed, you can resum it. You can do a few tricks to make this resummation easier, but you can do that and you see that you recover general relativity. But this time formulated as a particle or interpreted as a particle. All right, I confused you enough. I have shown you different ways how you could interpret gravity. Doesn't matter. Let's take general relativity and it's Einstein, so Einstein's field equation, and try to describe the universe. Now we try to build a model of the universe. So we have to solve Einstein's field equations. G mu equals T mu. This is the Einstein tensor that carries the dynamics of your metric. And on the right-hand side, you have the matter fields. Unfortunately, these equations are very, very complicated, highly nonlinear, and you cannot find exact solutions. So you need to introduce some assumptions, some approximations, and there the second pillar comes in, which is the cosmological principle. And this is the assumption that the universe is homogeneous, more or less homogeneous and isotropic on cosmological scales. Okay, which means that your metric satisfies certain symmetries. And if you do that, you obtain then these very simple equations, Friedmann-Lemaitre-Walker-metric ansatz here in the equations. Your equations become very simple in terms of the scale factor and the Hubble function here. And on the right-hand side, you see the energy density and pressure that represent the matter fields. And now you can find exact solutions to this simplified version of Einstein's equations. When you do that and you try to compare it with observations, what you see is that you need to introduce on this right-hand side in the T mean nu certain ingredients. This is dark matter, dark energy, and the inflaton field. So 3 unknown ingredients. But with these 5 fundamental pillars, you can then describe the entire evolution of the universe. And this is our lambda CDM model, the standard model of cosmology. Lambda representing the dark energy just by a cosmological constant, and CDM representing the cold dark matter. Nevertheless, there are some troubles of gravity, both theoretical as well as observational troubles. First of all, we don't know how to get our classical universe that we are observing from initial quantum fluctuation. This is a very challenging problem. So how did we start from this quantum fluctuation and had this inflationary epoch from which then all the structures formed? Another trouble is, of course, as I said, this 95% in terms of dark matter and dark energy, which we don't know what their origin is. So what is the fundamental source that giving rise to this dark matter and dark energy component? And even if you accept this picture, there are some observational tensions. This is something that I will be discussing on Friday in the structures seminar. So there is the so-called H0 tension and the sigma H tension within this lambda CDM model. So if you compare early universe cosmological observations with late time cosmological observations, then there seem to be some discrepancies on the constraints of the parameters of this lambda CDM model. Then we don't know how to reconcile general relativity with quantum gravity, so quantum mechanics or quantum field theory. We have some candidates, but we don't have a fully agreed theory of quantum gravity. And there are some singularities in our space-time, both when you look at the early universe cosmological scenarios, the Big Bang singularity, and also when you look at black hole solutions, you have black hole singularity. So there we know that general relativity as an effective field theory is going to break down, and you need to extend it. And you can consider extensions of gravity either purely classical or purely quantum. This could be string theory, when you are coming from quantum gravity and you're convinced that string theory is the fundamental underlying theory. But it could be also purely classical, some classical modification of gravity. Doesn't matter which way you go, you always introduce new additional degrees of freedom, new fields, besides the metric, besides these 2 degrees that are in general relativity. So this could be some additional non-abelian gauge fields, some additional vector fields, some additional scalar fields, doesn't matter. So imagine you come from string theory and you look at your low energy effective field theory, you see you have a bunch of particles, bunch of new degrees of freedom that you have to take into account. Therefore, let me introduce at least some straightforward extensions that you could do, both in the geometrical as well as in the particle perspective. In the geometrical extensions of general relativity, I showed you this trinity, right? The 3 equivalent formulations of general relativity. Now you can very easily take these 3 equivalent formulations and you promote them to general functions. So imagine you take the richest scalar and now you promote it to a general function of the richest scalar. Now you are not in GR anymore. You have modified gravity. Similarly, you can also take this torsion scalar and promote it to an arbitrary function of the torsion scalar. And similarly, you can also take the non-metricity scalar and promote it to a general function of this non-metricity scalar. Now you have three very different modified gravity theories that you could have considered, and they have very different properties. They have different number of physical degrees of freedom. They have different dynamics. They will give rise to different cosmological implications. Now, if you are in the field theoretical perspective, the easiest thing that you could do is you say, okay, I have my massless spin 2 particle, and now I add additional scalar field. And then you can construct scalar tensor theories. These are known as Horndenski theories. So on top of your massless spin 2 particle, you have now a massless spin 0 particle. Similarly, you could also add an additional vector, like photon-like degree of freedom, and you can have vector tensor theories. There, for instance, you could then construct generalized Proca theories. Or you could even add another additional spin 2 particle. Then you would end up having two tensors, and this is massive gravity. And so you see, you can put in many different ways these additional degrees of freedom, and then modify or move away from general relativity in these very distinctive ways. I will just introduce very quickly generalized Proca theories. How do you construct them? I will just write down the Lagrangians so that you are scared and leave immediately this place here. But it's just to show you that you can construct their Lagrangian by imposing some conditions. These are the conditions. You want to have second-order equations of motion, Lorentz invariance, and locality, and three propagating degrees of freedom associated to a massive spin 1 particle. And by imposing them, you can then construct these Lagrangians. Scared? Oh, no, you're still here. So you can order by order construct these self-interactions of this vector field. You can promote them to curved space-time and build vector tensor theories with some very specific dynamics, some self-interactions, some non-minimal couplings to the gravity sector, and so on. So these non-minimal couplings will give rise to modification of gravity. So you would then have, in the presence of these interactions, modified gravity theory. It was long believed that if you have one single vector field, that this is in contradiction with the cosmological principle that you cannot have homogeneous anisotropic universes. And therefore, that one single vector field would be not appropriate for dark energy application. But this generalized Proca theories initiated a radical change of view, because now with this vector field, with such self-interactions, you can construct cosmological solutions, where the vector field acquires a non-vanishing temporal component like this, and this allows now to have a homogeneous anisotropic solutions. Imagine you have this very simple Lagrangian. This is, you can agree, definitely simpler than the ones I showed a couple of slides ago. It's very easy that you can have dark energy fixed points independently of from which initial trajectory you started. They all go to this dark energy fixed point. And we have even shown that it reduces the H0 tension and delivers actually a better fit to data than the lambda CDM model. This was just an example. As you can imagine, I have shown you many, many different ways of modifying gravity, both from geometrical as well as field theoretical starting points. You can imagine you have a bunch of many, many different theories. Which one is it? You are probably biased, like me, because I have shown you the theories that I was working, right? But you might have your other favorite theories. So now it's going to be the task to test all these different gravity theories. And then you can do both theoretical as well as observational checks. Because my time doesn't allow, I will not talk about theoretical checks that you can do. this would be another hour that we could spend in order to rule out many of these theories. Let me instead focus on the observational tests and checks that these theories have to go through. Specifically, I'm gonna focus on the gravitational waves and the implications for gravitational wave measurements. So what is a gravitational wave? We have observed them, you probably have seen them. And so if I manage, I would like to show you a video of a good friend of mine, Umberto, who made this video. And it explains very nicely what a gravitational wave is.
What is a gravitational wave? It's a ripple in the fabric of space and time. Imagine that space is a giant sheet of rubber. Things that have mass cause that rubber sheet to bend, like a bowling ball on a trampoline. The more mass, the more that space gets bent and distorted by gravity. For example, the reason the Earth goes around the sun is that the sun is very massive, causing a big distortion of the space around it. If you just try to move in a straight line around such a big distortion, you will find yourself actually moving in a circle. That's how orbits work. There's not an actual force pulling the planets around, just a bending of the space. Gravitational waves are produced whenever masses accelerate, changing the distortion of space. Everything with mass and/or energy can make gravitational waves. If you and I started to dance around each other, we would also cause ripples in the fabric of space and time, but these would be extremely small, practically undetectable. Now, gravity is very weak in the scale of other forces in the universe, so you need something really, really massive moving very, very fast to make the big ripples that we can detect. How would you observe a ripple in space? If the space between you and me stretched or compressed, we wouldn't notice it if we had made marks on our metaphorical rubber sheet, for example, using equally spaced rocks, because these marks would also get stretched further apart. But there is one ruler that doesn't get stretched, one made using the speed of light. If the space between 2 points gets stretched, then light will take longer to go from one point to the other. And if the space gets squeezed, light takes less time to cross the 2 points. This is where the LIGO experiment comes in. It has 4-kilometer-long tunnels and uses lasers to measure the changes in the distance between the ends of the tunnels. When a gravitational wave comes through, it stretches space in one direction and squeezes space in the other direction. By measuring the interference of the lasers as they bounce between the different points, physicists can measure very precisely whether the space in between has stretched or compressed. And the precision needed is incredible. To detect a gravitational wave, you need to be able to tell when something changes in length by a few parts in 10 to the 23. It's like being able to tell that a stick 1 sextillion meters has shrunk by 5 millimeters. The effect of a gravitational wave is so minuscule and easily confused with random noise, you need a smart data analysis technique. Scientists hope to identify the patterns of gravitational waves by comparing the wiggles they measure in the experiment to the wiggles they expect from the gravitational waves. That's like trying to identify a song being hummed at a noisy party, a very, very noisy party. Imagine your whole life you had been deaf until one day your hearing was restored. You'd be able to explore the universe in this whole new way. That's why detecting gravitational waves is so significant. It's a completely new way of studying the universe. Anytime there's a new way to investigate the universe, we discover things we didn't expect. It's really about looking for new things we didn't know existed, examining the extreme edges of our knowledge of physics, and testing our theories about how the universe works.
All right. Thank you, Umberto, for this very nice video. Now we know what gravitational waves are. Yes. So what is a gravitational wave? These are ripples of space-time, and they give rise to changes in lengths and shapes, and we try to measure these super duper tiny changes in the length. You have seen in video, right, how challenging this measurement is. We do that using interferometers, and the measurement challenge is such that imagine you have an interferometer with a length of 4 kilometers. You try to measure changes of 10 to minus 18 meters, okay? And that's the reason why it took almost 40 years to observe the first signal of gravitational waves. So like the electromagnetic spectrum, there is also a gravitational wave spectrum. And using different instruments, we can then observe different frequencies of the gravitational wave signal. For instance, here for Lisa, this is going to be the frequency regime, which is going to be relevant. Here is LIGO, which is already observing. So different wavelengths will then probe different black holes of different sizes and neutron stars and black holes at different separation and lifetimes. So the goal would be to measure as many of these events as possible and combine this knowledge. So we basically test gravity by the shape of the gravitational waveform, these wiggles that we have seen in the video. These wiggles are basically encoding all the information in terms of the underlying parameters of your theory. So imagine you have different events with different sizes of masses and separation. And, oops, sorry. And due to these different masses and separation, you see you have a very specific waveform that you are gonna generate. And so by examining how this waveform exactly looks like, you can then see whether or not they have more or less equal mass or very different masses and how far they are. So you can then estimate the parameters of the underlying equation space. So what we need to do basically is compare the type of gravitational waveform that you would get from your specific theory to the observations and put constraints on the involved parameters. Okay, so you can, from the frequency evolution, you can infer masses, and from the masses and the amplitude, you can infer the distance, and from the time of arrival and the amplitude and the phase at detectors, you can even infer the sky location and so on. You can also observe some modulations. So you can, in principle, if you have a metric, you can have 6 independent polarizations, tensor, vectors, and scalar polarizations. What we need to do, essentially, again, solve Einstein's field equations. It always boils down to solving Einstein's field equations. But now we have a very complicated system of 2 massive objects with strong gravity, and it's very difficult to solve this system. And there we use different techniques. So when these 2 masses are sufficiently far away from each other, we can use perturbation theory. So we can apply linear theory and also post-Newtonian expansion, some nonlinear contributions as well. So we can do here perturbation theory. But when these 2 massive objects come closer and closer, close to the merger event, you cannot use perturbation theory anymore, and you need to really do numerical relativity, solve this system completely numerically. And then later, once the merger happened and you just have again a single massive object, you can use again perturbation theory. Okay, this is what I told you. You have perturbation theory, post-Newtonian theory, numerical relativity, and again perturbation theory. And you can combine that, and let's say you take this one from GR and you compare it to observations, and if the wiggles coincide, you know that this is your theory. And in the linear regime, this is a very simple physics. So you have some background metric on top of which this tensor perturbations, this gravitational waves propagate. And when you look at quadratic order in this perturbation, the Lagrangian always takes this very specific form. You have a kinetic term and you have some gradient term. And the term in front of the gradient term gives you the speed of gravitational waves. And this wiggles that we saw in the strain, the gravitational wave strain, has this generic form. It has an amplitude, which is frequency dependent, and it has a phase, which is frequency dependent. So we have this multi-messenger event where two neutron stars merged together. And this event was so special because this time they were not black holes, but they were neutron stars. And so when now neutron stars, collide and merge together, they don't just send the gravitational wave signal, but they also send the electromagnetic signal. And so comparing the arrival time of these two signals, the LIGO collaboration was able to put tight constraints on the gravitational wave propagation speed. So we now know that this CT squared parameter is basically the luminal, so is the same as the photon speed. It propagates luminally, but up to 10 to minus 15. So you see it's very, very tightly constrained. If your gravitational wave speed differs from that, you can already rule out these operators, these certain interactions. For instance, I was showing you the Lagrangian of these vector theories. If you have present these operators here, this would give rise to a non-luminal propagation speed of gravitational waves, if you want to use this guy as a dark energy model. Therefore, if you insist on luminal gravitational wave propagation, you see that we can get rid of certain operators. Okay, we can also have gravitational wave oscillations. So imagine you have GR and you have some non-abelian gauge fields, and these non-abelian gauge fields can have second tensor perturbations on top of the standard tensor perturbations that you have in GR. In the same way as also in massive gravity, you can also have their second tensor perturbations. If you have two species of tensor perturbations, you can imagine they can oscillate back and forth, like the neutrinos are doing. So you can then see how, due to this exchange between these two species, one tensor fluctuation and the second tensor fluctuation, how this is going to put imprints on your specific Beagle form. So imagine they have this very specific concrete friction term, such a coupling between these two tensor species. You see that this would give rise to a very specific modulation in your gravitational wave signal. And you could then directly test whether or not such gravitational wave oscillations are actually present. There's also something which is the gravitational wave luminosity distance that becomes more and more relevant, especially for cosmology. And this is the following. So by measuring the amplitude of gravitational waves, you get the luminosity distance of gravitational waves. In standard lambda CDM, this equals the standard electromagnetic luminosity distance, which is given by the Hubble function here. And you see that now by observing amplitudes of gravitational waves, we have a direct way, a completely independent way of measuring the Hubble function. Okay, and so gravitational waves serve now as standard sirens, and hopefully they will help with this H0 tension that I was mentioning that we are having now in the standard formulation of cosmology. So here's again this example when you have this non-abelian gauge fields and you compare these ratios between the gravitational wave luminosity distance with respect to the electromagnetic luminosity distance. In standard GR, in lambda CDM, this would be 1. But you see that if you have this additional tensor perturbation, your signal could have very, very specific form. And so this would be a concrete smoking gun or a concrete prediction in such a theory that you could then go on and test. Okay, if you want to know more about this different theories and how we can use different cosmological observations to test them, I am just putting here the link to my review article, and I finish here. Thank you very much for your attention.
Thank you very much. That's a stunningly simple, but also very complex, if you don't mind me saying. Simple in its implications, perhaps. I'm sure that there are going to be questions both from here and from the virtual audience.
Yeah, so the question was, you construct these theories, they probably underlie certain symmetries in order to construct this specific effective field theory. Whether or not there are other, whether the symmetries survive when you try to complete them in the UV. So the answer to this question is very difficult because we don't know what the UV theory would be. The only thing that we could do is we could try to impose certain symmetries that the quantum gravity should have. It could be, for instance, Lorentz symmetry, it could be locality, and things like that. And imposing these symmetries on the UV theory, you can then study what are the implications of your effective low energy effective field theory, and what type of operators are then allowed to construct. So there is not like a one-to-one correspondence, but there is a top-down constraints that you can apply. And actually, these are the theoretical checks or conditions that I was mentioning here. That would be in the theoretical checklist. There is, for instance, this request of positivity bounds that your scattering amplitudes of low energy effective field theories have to satisfy if you want to be able to be embeddable into string theory or into some quantum gravity theory. There are this swampland conditions that again comes from certain quantum gravity assumptions, and then you have concrete conditions on your classical operators that you have to satisfy.
You hear me?
Yes.
Hi, Lavinia. Thanks a lot. Very nice presentation. I'd like to ask your opinion about this CT, because we always, you and I think everybody, say it's the same as C, but of course we know, that that is only an observation at a rather local time. Yes. So it could be that was different in the past. So, and there are models such that this happens along an attractor, so that CT becomes equal to C asymptotically, but was not so in the past. So what are your opinion? Are we throwing away a bit too fast some operators in the Lagrangian, or you really believe that this is really justified to throw them away?
So, I mean, usually, you when you fine tune this general functions in a very specific way, such that you would have this one specific trajectory, and that gives you exactly the right propagation. I'm not sure, as soon as you move away from this specific trajectory, how this is going to be maintained. And also these functions, when you have such fine tunings, they don't have any symmetries. So they are not even protected, even from like a more fundamental quantum version. So me personally, I am always a little bit careful as soon as we have some very, very high level of fine tuning. But in principle, you could do that, yeah.
But as I say, so there are models which this is an attractor. So at least in principle is not fine-tuned. It just goes there automatically along all trajectories. There are.
So it's an attractor independently from which initial condition you start?
Correct. Of course, you cannot guarantee. Of course, you cannot guarantee that it happens already or that will happen in the future, as for every attractor. But this has this attractor property. So at least your objection that which I would agree in general, it's fine-tuning, maybe is not valid in such models.
Yeah, I mean, if you can manage that independently of any initial condition, independently of any functional form, that there is this attractor, then this is fine. Yeah.
Okay, thanks.
Thank you. reminded us how lambda CDM emerges from general relativity through Friedmann's equations, and it turns out that lambda CDM is really an excellent agreement with most of the data, supernova, VAO, cluster counts, and so on. But then there are deficiencies, and you just mentioned Hubble tension and sigma A. What is, from your point of view, the overall consistency of lambda CDM with data? Is it only these two deficiencies, or is there more that needs to be repaired?
Yes, yes. I think it's fair to say that lambda CDM works excellently well. I mean, it really works very well, and there are a few tensions here and there, other than the ones I mentioned, but they are usually statistically not so significant, always around 2 sigma or even below. So people then don't pay too much attention. But this H0 tension is becoming something that became significant compared to a couple of years ago, and now people are really starting to take it way more seriously.
Yeah, okay, do you hear me?
Yes, we can hear you.
Yes, so, one comment about the pillars of cosmological model is you have to add also a hot Big Bang to these pillars. But this was not my question. My question is that how the Lovelock theorem, how is it behave, or how is it stated when you have these other equivalent formulation of gravity?
So the Lovelock theorem is stating that you have when you are in the curvature, in curvature description, you have two propagating degrees of freedom. So you can only, and since you are in the curvature perspective, you can only work with the Riemann tensor, and then the Ricci scalar is the only thing that you can have, right?
Yeah.
And so the Lovelock theorem is about the uniqueness of this term, and the same Lovelock argument you can then say about the uniqueness of this Lagrangian, which is now quadratic in the non-metricity tensor. So it translates 1-to-1. You have to tune these coefficients in this very specific way here. In the same way, you had to tune your specific coefficients here. This -1, this -1, this +1. You had to tune them as well in order to get exactly the Ricci scalar. So the Lovelock theorem, if you want, is about the specific tuning of these operators.
Austin, thank you so much, Lavinia. That was such a thought-provoking talk, and thank you very much. And we wish you all the best in this very interesting exercise, and we look forward to the next decades and how the observations are really going to pin all this down. Thank you so much.
Thank you.